So I want to tell you about a problem that I have because I think it actually highlights a really deep problem for the field of psychology. And the problem is that every time I sit down to try to write a manuscript, I end up eating Ben and Jerry's instead. So I sit down and I really try to focus on what I'm doing. And then this voice comes into my head and it says, "How about Ben and Jerry's? Now you deserve it. You've been working hard for almost 10 minutes now." And then before I know it, I'm on the way out the door, down the street, and I'm getting some ice cream for myself. So this is a problem for psychology, not, regrettably, because I was writing anything terribly important, but rather because it highlights a really deep tension in a theory that some of you are going to be familiar with, a kind of dual process theory of the mind. So from one perspective, it seems like this sort of competition between more automatic and more controlled processes gets cashed out in terms of willpower. And through the willpower lens, one would want to say that my desire for Ben and Jerry's is the product of automatic or intuitive responses, literally gut feelings in this case. And then it's a controlled, effortful, deliberative process that tries to focus on the paper and put thoughts of Ben and Jerry's out of mind. But on the other hand, it would truly be bizarre to say that when I went to Ben and Jerry's, it was an automatic response. I mean, I have to go through a process of goal-oriented planning. I've got to get my shoes on. I've got to get out the door. It's not like I was sitting at my computer and then 1 minute later, just out of habit, I was suddenly eating, coffee ice cream at Ben and Jerry's. And so it doesn't fit together, right? So there's this kind of mismatch between the willpower perspective and between the sort of goal orientation perspective. And I'm not going to solve it. But what I want to suggest, the exciting part, because I'm going to get ice cream instead, and I'll see you all later. The exciting part for me is that I feel like we're finally able to at least frame the questions in the right way, such that an answer's in the offing. And the questions are being framed these days, I think, by some really foundational work that went on in computer science when people tried to design artificial intelligence systems that could learn and decide. And they drew a division between two broad classes of solution. So one of them, which has been worked out best and is very familiar to psychologists, is a kind of stimulus-response learning based on reinforcement history. So here I want you to imagine a rat that's in a Skinner box. It stumbles on a lever once. It notices that a food pellet comes out. And so it forms an association between the environmental context that it's in, being in the Skinner box, and pushing that lever. And the association is sort of between that action and value. So it says, whenever I'm in this box, the valuable thing for me to do, the stimulus is I'm in the box, the motor response is I'm going to push the lever, that's a valuable thing. Now, remarkably, you might think that the association that the rat would form would be between pushing the lever and getting food, the outcome of its action, but it turns out not to be the case, at least some of the time. You run a procedure called a devaluation procedure. So you put the rat in the box, it forms the association between pushing the lever and value, and then you take it out of the box and you give it unlimited access to food pellets until it wouldn't touch a food pellet with a 10-foot pole. It's completely stuffed. And then you put it back in the box, and under the right conditions, it waddles over to the lever and pushes it, and the food comes out, and it just lets the food sit there. So you know that the rat wasn't pushing the lever because it had a goal in its mind, and it associated pushing the lever with a particular outcome. Rather, it's a stimulus-response association. I'm in the box, pushing the lever is good. And what the computer scientists were able to do was to formalize mathematically the kinds of representations that support that kind of learning. And then in a way that I won't have time to describe right now, they showed how you could string together series of stimulus-response associations to make not a far-sighted decision would be the wrong way of putting it, but to make local decisions that have long-run consequences that are good. Okay? And it turns out that once the computer scientists formalized this stuff and they had the equations that specified, there'd be a parameter here, there's an alpha, there's a gamma, and then you go look in the brain, while people are making decisions in these types of tasks, you find that if you ask, are there voxels in the brain, are there regions of the brain whose response profile tracks those precise mathematical parameters, they do, again and again and again. It's happened hundreds of times now, mostly in the basal ganglia, which is a brain region we know, for instance, is impaired in Parkinson's. You think about what goes wrong in an individual with Parkinson's, they're not able to produce motor actions. So this is a part of the brain that's responding to stimuli, and it's producing motor actions. And when it's disrupted, you can become literally put in a kind of a frozen state. Okay. So we understand that system pretty well. But it's obvious that tons of human behavior is exactly the opposite of that. It is goal-oriented. And in fact, the rats do this too. You can have other conditions in which you put the fat rat back in the box, and it doesn't touch the lever if you run the experiment appropriately, because now it's operating in a kind of goal-oriented planning mode. So it has a particular outcome in mind that it wants to achieve. In this case, the outcome is not food. Maybe it's just sitting and digesting. And then it selects the actions that are appropriate to get towards that goal. And computer scientists have been able to formalize algorithms that do this type of goal-oriented planning as well. The problem with these algorithms is that if you make a task even moderately complex, they totally fail because of the computational intractability of planning. We brought up the case of chess earlier, right? So chess is a game where there's many, many opening moves, and then there's many, many next moves, and then there's many moves after that. It's perfectly obvious what the goal is. You want to get to checkmate. But there's so many possible paths that you could take that you could have all the time in the world, and that wouldn't be enough time to evaluate each one of those paths independently. And this is a really deep problem for computer science and also for psychology. How we know that humans use goals, but how do you get goals off the ground? How do you get this planning process off the ground and make it computationally tractable? So there's a couple of solutions that people have focused on to try to do this. One of the solutions is to arrange your goals hierarchically. And I'm going to use a metaphor here. I hope it's a hopeful one. Imagine that we took a picture of this group and we turned it into a jigsaw puzzle. You can suppose one way to try to solve the jigsaw puzzle would be to randomly arrange the pieces one by one, as if we were taking random searches down that chess path, right? You'd have to go through billions of random arrangements before you ever alighted on the appropriate one. But if you organize the puzzle hierarchically, you could reduce that search space a bit. So you'd say, I'm going to just focus on Josh. I'm going to just take the pieces that look like they plausibly belong to the Josh area, fit them together, and then the June area, and the Rob area. And then once I've got those units organized, then I can shuffle high-level units. And so you don't have to try every combination anymore because you're working on little local problems and then moving big chunks of space around altogether. So that's a good start. That helps. But it's not going to get you the whole way. Because still, even just a simple task like making a sandwich, I can say in order to make a sandwich, I'm going to have some kind of sub-goal. There's going to have to be a first step. But there's kind of an infinitude of next steps that I could take. One of the next steps that I could take would be to get the bread out of the refrigerator, but another next step that I could take would be to start the manuscript that I have to start, or to pick up my wife at the train station, or an infinite number of sub-goals that a person could possibly entertain. So we're going to need some kind of a cognitive system that, in the state of having a goal, selects the appropriate cognitive action of selecting a sub-goal. And an insight that occurred about a decade ago in psychology was that you could actually maybe use the basal ganglia, that old rat-like stimulus response learner, to solve that problem too. So here's how it works. When we talk about the rat, we talk about the rat being in the perceptual state of a Skinner box and having learned the motor action of pressing the lever. But by analogy, you could say that the rat would be in the internal perceptual state, the kind of conceptual state of having the goal of, say, making a sandwich, a very smart rat. And then what the basal ganglia has to learn is a particular cognitive action rather than a motor action, which is the appropriate cognitive action in that conceptual state. So you could learn that when you're in the conceptual state of wanting to make a sandwich, the next cognitive action to take is to select the sub-goal of getting bread and load it into the goal unit. And then if you're in the cognitive state of getting bread in working memory in your sort of goal slot, then the next cognitive action that you're going to take is walking over to the refrigerator. So this is a way of using the kind of simple machinery that we understand of stimulus response learning and getting it to perform the individual computations necessary to do a much more sophisticated type of goal-oriented planning and action selection. And one of the remarkable things is when you go back to the Parkinson's patients who are not able to produce motor actions, and you ask them what it's like to be in that state of being sort of frozen in this motor sense, they'll talk about feeling cognitively frozen too, as if their thoughts are moving with incredible slowness, or they can't bring the thought to mind that they want to bring to mind. It's quite different than other types of motor impairments, like ALS deprives someone of the capacity to produce a motor response, but their thoughts are moving just as fast as they ever were. And so a bunch of research has now shown that region of basal ganglia is interacting with working memory in order to facilitate the movement of information in and out of working memory. So there's a few things that I find kind of exciting about this. One is that I think one of the markers of progress in psychology is when you can exorcise just one of the ghosts from the machine. When you can take one of those points in science where you had to say, and then a miracle happens. Like, we knew we had to make a sandwich, so the obvious sub-goal was get bread. But that's a little bit of, and then a miracle happens. I mean, how did you actually get from point A to point B? And this starts to show us the way that you can do that. The second thing that I like about it is that it teaches me something about why it is that I keep ending up at Ben & Jerry's. Right? And the idea is that my basal ganglia has learned that when it loads the sub-goal, get ice cream, into working memory, good things happen, right? And so when I'm trying to work on my paper, what's happening is that this basal ganglia that really loves ice cream keeps saying, oh, you know what would make me happy? What if you had the goal of then going and getting some ice cream? And what that suggests, this is kind of the third thing that I love about this area of research, is a new way of thinking about what automatic and controlled processes are and how they relate to each other. For a long time, we've talked about automatic and controlled processes as if they were systems, as if we were going to go into the brain, perhaps, and actually find completely dissociable mechanisms. One of them does the dumb stimulus response learning thing. Another one of them is going to do the smart goal-oriented planning thing. What this suggests is that the controlled processes are really just a kind of an adjunct. They're an add-on. They're an optional feature, like an app that you can run on the lower level stimulus response system. Specifically, what they do is they take a system that probably evolved to mediate between perceptual states and motor actions, and then turned it inwards and allowed it to operate on conceptual states and cognitive actions. And it feels actually deeply true to my intuitions about how controlled cognition works. Let's take a classic example of a controlled cognitive process, say doing a calculus problem. Okay. Well, maybe let's make it simpler. Let's just make it long division. So if I think through long division, the individual cognitive operations that I perform each seem to bottom out in a kind of a habit or an intuition. Like eventually I'm just going to have to say that 5 minus 3 is 2. And it's not as if when I get to 5 minus 3 is 2, I'm still doing something controlled. When I get to 5 minus 3 is 2, I'm in a conceptual state, 5 minus 3, and then almost habitually 2 just pops out as the answer to that question. And if you think back to, when you were in kindergarten, you actually had to learn that cognitive habit the same way that the rat has to learn about pressing the lever and getting reward. That is, the teacher ran laborious drills on your times tables and on, the shortcuts of division and the specific operations that you would have to perform at each step in the process of doing long division, right? So these are the things that I kind of, that excite me the most about this area of research and reinforcement learning and the ways that it connects with neurobiology. Now, I said at the beginning that I regard this research as a kind of a promissory note, that where we are right now is that we're starting to be able to frame the questions in the right way, but that a lot of the answers are still elusive. And it might seem as if maybe I'm overselling the research because I've been presenting some of these ideas as if we had all the solutions worked out. And I want to start by saying, well, we don't. I mean, people have a hunch that it's going to work something like this, but getting all the nuts and bolts to fit in place is still to be done. But there's also a much, much deeper question, which I think has largely been ignored, and is one of the areas that I'm excited to move into over the next couple of years. And what's been ignored is where on earth I suppose the way to phrase it is, it's the learning problem of getting the right cognitive stimulus response habits. What do I mean by that? So when we plan very complex things, like John planned this lovely weekend for us, and there's a lot of pieces that had to come together, from the film crew to the specific set of speakers to getting these tablecloths and the tables. When we're putting together something as complex as that, is it really plausible to say that John himself learned each of the appropriate cognitive stimulus response habits such that all of these things that have never interacted in this way before would fall into place perfectly? Right? John in his lifetime just hasn't had enough experience. Well, I shouldn't say this about you in particular. I suppose that even, some of the younger of us around the table could have put together something like this, but we wouldn't have benefited from the experience that John has had through his lifetime putting together many such events. So what's going to be the source? Where would the knowledge come from that we can then flexibly assemble into novel plans and novel procedures? A hint towards the solution to this problem, I think, comes from observing that humans as a species we stand apart from all other species in our ability to engage in controlled cognition, to organize our lives around very distant goals, to inhibit more automatic responses and hold and use flexibly information in working memory. So we should ask ourselves, what is it that enables humans to do that? What are the other things that are unique and special about humans that might explain why we're able to engage in controlled cognition? The one other thing that stands out to my mind as being incredibly unique about humans is culture and is social interaction. And one obvious source, and it comes back to the point that I made about how we learn to do long division in school, one place that we could learn the appropriate sets of cognitive stimulus response actions, the ways to manipulate information internal, held in working memory, would be through the scaffolding of other people teaching us and other people showing us, if you want to get a PhD, you're gonna have to publish a certain number of papers. And in order to publish the papers, you're gonna have to run the experiments, and you're gonna have to be able to run a t-test, so you better go to statistics class, right? We can't learn all of that stuff through trial and error. Like the first time I tried to get a PhD, I didn't go to statistics class, so let's try something new this time. Right? That knowledge comes to us through cultural channels. In the literature right now, there's a debate between two rival theories for what makes humans unique. One theory calls itself the cognitive niche. And it basically says what makes us unique is that we can think very, very carefully and hard about things in a controlled way. And another hypothesis calls itself the cultural niche. And it says, no, what makes us unique is that we get for free the answers to problems culturally. Other people have worked it out through trial and error, and they tell us. What I find really exciting is the idea that it's not just that both of those things are true, but that they're codependent. That in principle, you could not make the mathematics of controlled cognition work. You couldn't solve the computational intractability without the support of cultural input. And that the cultural knowledge wouldn't be much good if you couldn't flexibly reassemble it in the way that hierarchical representations allow you to. So that's a promissory note. We haven't done the research yet. I don't think I haven't. I certainly don't think the field hasn't either. But that's what I see as being really exciting right now. And in a way, if we were able to use some of these ideas to address the problem of what it is that makes humans so different than other organisms, it would be rather more exciting than just having figured out why it is that I keep eating ice cream instead of writing papers.
Thank you.
Yeah.
How does your treatment relate to the Newell and Simon idea that basically you solve problems by working backward from where you want to go? That is, if I want to go there, I must get here first.
I think that there's a lot of virtue to thinking about working backwards. Introspectively, I think all of us do this a lot, but you still have the same computational intractability problem. If where I want to be is having a PhD, And there isn't some trick, there isn't some ghost in the machine that's going to help direct my attention to, of all the things that could directly precede my having a PhD, the one which is relevant, which is having written at least 3 papers. Then I've got an enormous search problem on my hands. So whether you're moving forwards or moving back, I mean, you see, my point is, you could say, oh, I want a PhD. What's going to be important? Let me start with the A's, having aardvarks, alpineering, that you've got an enormous search problem. You've got to constrain that space somehow. There's got to be some part of the brain that is able to direct your attention to the correct response, given the cognitive problem that you have, this sort of cognitive state that you're in, whether you're moving forwards or backwards. Another way of thinking about it is, could we go to the programmers of Deep Blue who are trying to design a computer that plays chess very well and say, oh, you guys, couple decades of work, just go backwards. Start with checkmate, work backwards, right? But it's not that easy.
Well, I mean, you would know that people who get a PhD have something in common. I mean, that is something in your experience, and you get that culturally.
Yeah.
And so that would very considerably narrow your search space.
That's right.
That is, people who get their PhDs, if you look backwards, they all took prelims, they all wrote a thesis. I mean, there's actually a lot that you know from the fact that somebody got a PhD that allows you to go backward. It's not, start with A.
That's right. And so I think there's 2 important conclusions to draw from that observation. One is that it's certainly not the case that having learned it culturally or in school, it would be the only answer to how we could narrow that search space and find an appropriate solution. And that, I wouldn't suggest that it is. But the second point is that suppose that by hook or by crook, one did know that the appropriate step before getting the PhD was having 3 papers. What brain mechanisms would one then use to codify that knowledge and allow it to be used when next planning to get a PhD? The PhD case is tough. One only does that once, hopefully, but making a sandwich, it's something you're going to do every day. You want to cache that knowledge somewhere. Gary Marcus has this wonderful title for a book of his, Klooge, and the basic idea is the brain has a bunch of pieces sitting around and you're just going to klooge one of the pieces you've got. And it looks like at least one of the klooge solutions to where you would cache that knowledge is in the basal ganglia through this kind of analogy between the perceptual motor linkages and conceptual cognitive linkages. Almost certainly not the only way that people cache out that type of information, but one of the ways that we've begun to understand and that I find exciting.
There is direct evidence that the basal ganglia are involved in that?
Yeah, absolutely. So for instance, my colleague Michael Frank has this really beautiful work where he takes Parkinson's patients and manipulates whether they're on or off L-DOPA, and then looks at the impact that has on their ability to use working memory representations, or looks at people with different genetic variants that impact dopamine function in the basal ganglia, and again shows systematic effects on working memory. Where I'm pushing a little bit beyond, and I say this as a warning, not as a self-congratulation, where I'm pushing beyond this, I think the sort of state of the art in the field, is in suggesting that one of the most critical functions of those working memory representations may be to solve the problem of hierarchical goal planning. So he's used NBAC tasks, very standard measures of working memory, but ones that don't necessarily involve hierarchical representation. But folks like Matt Botnovic and David Better have been starting to take those models and say, these look like just what we need in order to understand hierarchically embedded goals. And that, who knows, it may go flop, but I think it's got a lot of promise.
Yeah, so I love this stuff, and I particularly love the cultural angle, but it strikes me that there's some empirical stuff that we might not know yet, or maybe if we know it yet, which is the extent to which your social inputs and other people's social rewards can feed into these reinforcement learning models, right?
Yeah.
So there's one question about whether I can watch other people getting rewards, and whether I can structure from that my own set of plans, my own kind of perceptual and motor kinds of schemes, because ultimately if that social input's going to get in there, it strikes me that from your argument, it has to enter in the kind of dumb rat level as opposed to the kind of goal level.
Yep.
So do we know, can you get reward prediction error from other people's rewards? Are people looking at this stuff yet?
Gosh, I'm embarrassed to say that I don't know right off the top of my head for reward prediction errors. The best work that I know on this topic is by Liz Phelps. and a lot of her work focuses on aversive or fear conditioning rather than, she has some stuff on reward too, but fear has been the mainstay of her research. And so she has some work showing that the amygdala, which seems to play a somewhat analogous function, these sort of conditioning processes in the fear domain, responds equivalently so in one experiment, you're hooked up to a shock machine, and a computer shows you different shapes. Whenever you see a blue square, you get a shock. Your amygdala starts to activate whenever it sees the blue square, even absent the shock, because it's formed this predictive association. So she finds that you can show somebody a video of somebody else participating in the experiment, and then if you show them a blue square in the scanner, you get the same amygdala response, even though they've never experienced it themselves. They've only seen it through the video. And she additionally finds that you can get a similar response just by telling them, hey, you know what about blue squares? They predict shock. And then but the interesting thing is that unlike when you observe it directly, you get a bilateral amygdala response. When you learn it verbally, you only get a left amygdala response. And of course, a tantalizing possibility is that language is left localized.
That's lovely.
So I really liked your example about the rat that when the rat doesn't want food at all, it will still. So according to the theory that you've been developing, it should be that same thing that the rat is exhibiting in its behavior, we should be exhibiting cognitively. That when we're even though we don't exhibit the behavior actually, when we're just trying to figure out what should be my sub-goal, we're going to show that exact error.
Yeah.
So do people actually do that?
So you've drawn me into inside baseball, but yes. I think we do, and I think the best example of it is actually in the moral domain. We consider it worse to harm somebody as a means to an end than as a side effect of our behavior. So an example of this, for instance, the Catholic Church has a very peculiar version of this doctrine, in which if you are pregnant and your fetus presents a threat to the pregnancy, then it's impermissible to terminate the pregnancy in order to save yourself, because you're killing the child as a means to saving yourself. The death of the child is the mechanism by which it's the sub-goal, right? It's like, what's threatening me? Child. And then the sub-goal is kill the child in order to avoid the threat. However, if you're pregnant and you develop uterine cancer, the only way that you can save yourself is to have a hysterectomy, but as a side effect of the hysterectomy, of course, the pregnancy will terminate. That's permissible. And notice the one critical difference between the two cases is that in the hysterectomy case, there's no sub-goal. You didn't say, oh, my sub-goal, in order to achieve the goal of saving myself, has to be to kill the child. So people draw a distinction between these two things. I hope you can see the way that this connects with some of the ideas that I was describing before. If you had a system that assigned values to sub-goals, then that system, when it looked at the sub-goal, kill a child, I mean, of all the things to assign a negative value to, that would be very high on the list, right? And so you'd get a big response out of not wanting to do that. But when it occupies the role of side effect, a system that assigns values to sub-goals would miss it. What's interesting about that case, and again, it comes back to the challenge of working out a kind of dual process view of the mind. Usually when we think about goal-sub-goal hierarchies, we think we're in the part of the mind that's fully controlled, that has promiscuous access to all knowledge in the brain. But a system that was fully controlled and had promiscuous access to all knowledge in the brain would focus on the fact that the baby's equally dead in both cases, right? So you have to understand, why is a sub-goal representation really critically important, and yet important in a blind way, right? Important in a way that can't put together all the consequences in a kind of forwards planning sense of an action that we take. And if you think that there's this sort of peculiar marriage between a relatively more dumb system that just does the stimulus response stuff and places values on actions, including sub-goals, and then the process of goal planning itself, I feel like you might be able to have your cake and eat it too.
Danny's question got me worried, because I found your chess metaphor very appealing, then your question about working backwards made me realize it's actually, I'm worried we're over applying the math implicit in that metaphor. So picture the chess tree. It's actually a tree that's exploding out.
Yeah.
And when you say we want to reach checkmate, the reason
There's many instantiations of
Many
checkmate. Yeah.
on the other hand, there are many mathematical problems, like the puzzle example you gave, exactly does not fit that. There is exactly one instantiation by which the puzzle is assembled.
Yeah.
So the idea that there's this nature is kind of an illusion. There is this thing, and of course, then working backward makes total sense, which I think is what you were getting at with your PhD example.
Yeah.
And is that just a superficial problem? Is that a more basic distinction between these? And I know in the actual programming literature, these are two very different kinds of things, and and everything in between happens. But is that notion that there are tasks where there is only one thing, there is a thing you're trying to get to, so you can work backwards, versus tasks where so many things can lead there, and the end goal is that distinction important? Is that something people have thought about? Because the math would be quite different.
I mean, the wonderful thing about having started this discussion by saying I'm going to present questions that I find exciting rather than answers is that I can now say I just don't know. I think it's a perfect question, and I don't know the answer.
The other question I have is and your language thing may have already answered this, so I'd love to know, is that I love the long division thing and the idea that you have truths, 5 minus 3 is just 2, sort of this rote learning thing that I kind of, but yet, and maybe this is just an illusion, but it feels to me that some amounts of my sort of almost automatic cognitive responses, it's not just that they were never learned by me, as you were getting at.
Yeah.
It's also they were never rehearsed in this way. Even if they were learned by Danny, who told me, it's not, he didn't tell me and tell me again and again, and there was no rehearsal. I didn't, in my mind, rehearse the thing again and again and again until I got it. It was almost like I got that module, sometimes from someone else, sometimes just by figuring it out and saying, oh yeah, this is the right thing to do. But once I had it, it was almost like I could pop it as a system.
Yeah.
And it felt like it pops into a system, and maybe this is what we'll discover, is it doesn't pop in the same way as something that was rote learned, but at least by my own intuition, it feels as automatic as 5 minus 3 is 2.
Yeah.
Yeah.
And so, how do you think of, do you see what I'm getting at?
I do see. I mean, I think one of the areas of research where people have really investigated that pop-in effect is what gets called fictive rewards. So Reed Montague is one of the leaders in this area of research. So the idea is, in the simplest version of making a person into a rat, you just give them a bunch of levers they can pull and they get rewards. So if they pull lever A, they get the reward from lever A, and over time they learn which levers are good. But a somewhat more complicated version that reflects the way that humans sometimes learn about things is that when you pull lever A, you get reward B, but then it's revealed to you what reward you would have obtained had you pulled lever B or lever C. And behaviorally, you observe that people use that information. Quite sensibly, they should. It turns out that when you look in the brain and you try to look at neural systems that seem to be responding to those moments of revelation, it's the very same mechanisms that learn from direct experience. So what the prefrontal cortex seems to supply is a fictive reward that the basal ganglia then treats as if it had been a veridical reward, so that on the next time you have to choose one of these 3 levers, the basal ganglia itself can evaluate their relative values. And again, I really don't want to give the impression that that is the complete answer as to how humans behave in gambling tasks. It's certainly not. But at least with respect, the beautiful thing about the basal ganglia is we've learned an awful lot about how it works. So at least with respect to that system, we know that there's a way that you can take a verbal representation and somehow create the type of input to the system that ordinarily a reward occupies, even though no reward was experienced. Is that?
I mean, it's like you had said, sort of exercising the ghost from the system.
Yeah.
It feels like, to me, that particular ghost would be very interesting, because when you start talking about conditioning, I thought, wow, this is really interesting. We're going back to this but now we have this ghost creeping back in that feels totally different and interesting. I mean, I'm not saying we haven't made progress, but it feels like that ghost would be a particularly high return one to kind of
return one.
to like figure out what does that thing look like.
I mean, some of the most exciting stuff that's happening now working on that problem. For instance, there's a and I'm so embarrassed I've forgotten the researchers who are responsible for this work, but a team has used optogenetic techniques to be able to selectively activate neurons within basal ganglia that respond to reward. So now they can be the ghost. That is, they can direct the response of these neurons and then observe the subsequent impact on behavior, where the rats prefer lever C because just at the right moment in time they juice the lever C neuron. But that's a long way from answering how one's own prefrontal cortex does it. Yeah, exactly.
Good place.
Good. Thanks very much.
Thank you very much.